morning, everyone, and welcome to the NOC. Today, I'm going to talk a little bit about unusual topic for oil spill monitoring. My approach to this: do not let it happen. So we target the problem before it's actually happened. I'm Royal Academy of Engineering fellow studying pipeline inspections, so making photonic sensors, laser-based or light-based sensors to monitor the detection of hydrocarbons for the applications of oil leak detection.
Can you just speak into the microphone? Thanks.
So I'm going to talk about Southampton today. So I come from two institutes. So my host institute is the University of Southampton, where we're proud to have the state-of-art clean rooms. Let's keep moving.
Yeah, I don't know why.
It's okay. I'll go back. So these clean rooms, we do all sorts of nanotechnologies. These little sensors, light-based sensors or lasers, that are capable of replacing these bulky and big ocean sensors that we use nowadays. So the vision of my research is replacing lots of these sensors within the next 5 years, but also, most importantly, giving a brain to these vehicles that you talked about. And by talking about brain, I'm talking about these sensors and some AI as well. So we can try to find and follow the source of the problem. I'm not going to talk too much about the NOC, so hopefully you'll see yourself about our capabilities in the tour this afternoon. But I'm also working in the Ocean Technology and Engineering group, where you talked about clear waters, some of the nearly commercialized technologies for ocean monitoring. So we measure different type of analytes, ammonia, pH, and nitrites. And we're trying to expand this to a new level of chemicals. And these new chemicals are what will enable us to measure these leaks in hydrocarbon detections. Now I'm going to talk a little bit about my institute and the other side of Highfield, the Optoelectronics Research Center. Back in 2005, we had a big fire that unfortunately destroyed all our infrastructures. So we had to start again from zero. This actually was not a very bad thing. It turns out to be a good thing. So we created what is parallel to the NOC in terms of ocean monitoring, but something top class in photonics engineering, so laser engineering. And this institute is one of the top countries in the world, one of the top institutes in the world of manufacturing these devices. So when I talk about lasers and photonics, I'm actually talking about optical fibers that's already underwater, delivering the optical signal to your mobile phones and networks. The ORC is one of the main contributors and inventors of these optical cables. Another area of strength is silicon photonics, which you can find this in your mobile phones and then in our computers and laptop. It's basically everywhere. And we're proud to say that the ORC has also large influence worldwide with these technologies. So what I'm hoping to say is that we did great for telecoms in the past. Now with this nearby location for both institutes, it is time to focus on sensing, especially for ocean monitoring. We could use all these technologies for ocean sensing, including oil spills monitoring. So this is some of the capabilities that my research group are working on. Optical fibers. We have the biggest optical fiber towers in the world that has been, again, used for communications. And now within my group, we're looking only at sensing. So it's a new capability that emerged 5 years ago. So I've been asked not to be technical, and this is extremely challenging for me. But I just wanted to talk about the principle of what I'm trying to do here. All these sensors that we use is based on large bulky elements because it have light source and a detector. And the field in between them is that what we're trying to detect. All these equipments are designed for air, to be working in air, not underwater. And that's what makes them actually quite big, because if you put them in the water, they will collapse straight away because of these air gaps between them, because they are designed in air. What we are trying to do now is to design them for water. And actually, if you design them properly, you will end up with something extremely small that will fit in any of these autonomous vehicles, and then capable of doing autonomous sensing. So I mentioned this before. What we are trying to do is use these robotics. I partner with EcoSub, Planet Ocean, to try to make the sensors as small to go to the cone head of the Earth of these sensors. I believe that the UK, maybe actually worldwide, we invested a lot in robotics, but not enough yet for sensors. So we need to use this vehicle that can actually already reach the middle of ocean to make it a little bit smarter and be capable of making decisions of where to look for and inspect the problem. By problem, I mean leaks. So my main work is focused on methane sensing, and you can straight away think why I'm here. I'm talking about hydrocarbons. So I'm mainly interested about the pipeline leaks, but as my work started, I collaborated with lots of people for science as well. I realized that the problem is much bigger than we anticipated. In order to find the leak, you need to find the baseline. What's the actual real concentrations of these hydrocarbons without a leak? These are still data not very available all over our oceans. So this is the first step. We need to get these baselines right. And then also the issue related to methane hydrate is another problem that one of my PhD students are looking at. So this is what I mentioned before, just a quick demo about lasers and detectors. So this is, I hope you don't realize what this equipment is, but it's one of the current technologies, one of the leading technologies for hydrocarbon detections. And you can see it's quite big and bulky simply because what we have been doing in the past 20 years, we shine a laser on a detector, monitor the signal change as you find some hydrocarbons. That's it. Then we try to become a little bit more clever. We put some mirrors. The mirrors made the lights bounce back, and then we increase the sensitivity for measurements. So thinking outside the box, I guess, we don't do this anymore. We don't need to do this. So we reinvent this technology by using this nanophotonics. So what do I mean by nanophotonics? First of all, we don't need to use lasers. Lasers nowadays are on chip scale. Then the sensing medium, we don't really need to use air, since air is our problem that's making the whole air thing very bulky, because we'll need pressure caging to prevent it from collapsing. And detectors also became very small. So just by replacing air, which is our problem actually, with these nanophotonics technologies, we're solving the problem of size and the cost by 2 orders of magnitude. I think actually it's 3 orders of magnitude, but my boss made sure that I say 2 orders of magnitude in order not to overpromise. So all these lasers, detectors, and waveguides are manufactured in the university clean room, which is just a mile away from the NOC. And this is to show what is happening now, what we're doing. We are scaling down the technologies quite a lot from these bulky technologies that does not fit autonomy yet, to something very small. It's a silicon photonic chip integrated with all these detectors and lasers. So I promised not to be technical, but I have to say that this is something I'm extremely passionate about. All have been done so far is working in mid-IR. So these technologies are very new, it's very big. And it's basically target the absorption lines of these molecules. So when I talk what's absorption lines, each molecule will have a fingerprint, just like we do have our own fingerprint. So mid-IR had strong massive absorption lines, and all current technologies actually based on these mid-IRs. What we're trying to do is actually avoid going too far and too expensive, but use the advances that telecoms have done, the telecom wavelengths, so optical fibers again. With the technology already exists, the fingerprints are much weaker, but we can amplify it. And this is what we're trying to do in one of our projects. So definitely both, in my group, we're looking at both venues near IR and mid-IR. And this is the spectrum of light where we're looking at the analytes. Yeah, so as you can see, I'm not talking about something that we can we have used before. It's something we hopefully will go to the water and scan in high levels in the near future, and with the potential of enhancement by orders of magnitude within the next decade. So how does these sensors work? So this is one of the sensors that I first started developing when I joined the NOC. I just want to talk briefly about how it's worked. If you imagine you're sitting in a train and you put your hands out of the window, you will straight away feel the cold, or if it's raining or whatever. This type of sensors do exactly the same way. It guides the light. The light is confined within, but it can also sense what is in the surrounding. And actually, you can control how much light can go beyond the physical dimensions of your sensor and how much you want it to interact with. And this is why I am very curious about using these technologies for oil spill monitoring, simply because we don't need to get too close to the pipeline, for example, or the source of leak, in order not to cause any damage or any more damage, because you control the depth of the light that's going. It can ping and come back. Now, I use the word ping because this is what's used a lot in current days technologies with acoustics, but this is lasers. I'm talking about lasers, so the speed is few orders of magnitude faster, way much smaller as well. I'm not going to talk too much about the details, but this is the sensor itself. It is tiny. It's the same size of 1 pound coin. The cost is around 20 pounds. I'm not sure if I calculated the cost very well. As you can see, I'm a scientist, not a commercialization person.
It's 3 times that, right?
There are two types of I'm now going to talk about what's available today, what we can use today, and what we can use in the near future. So these sensors that we have ready at the moment at the NOC, and it is part of our capabilities. We talked about putting our hands outside of the train to detect something, but I actually don't want to detect everything. I want to detect something only, which is hydrocarbons. So in order to do that, we need to have something selective to put on the sensor to detect only this hydrocarbons, only this type of hydrocarbons. I'm not going to go too deep in the details, but this is how we do it. However, the problem with this, we rely on the selectivity of these molecules on external partners. So this is why we cannot promise yet in a large scale. We had a huge success in the past year of making these molecules in Southampton in the chemistry department, again, 1 mile away. But this is one of the technologies we have, and as you can see, it had a fantastic response for hydrocarbons. We started with integration these sensors with EcoSub. With the EcoSubs, as you might know, a lot of these vehicles are very expensive, and people do not want to hack their brains or. Yeah, so it has been challenging, but I've been collaborating with the Planet Ocean, with the EcoSubs, and I feel this is the proof of principle that we're looking for, which is what we need for the scans. Again, this is the sensors we have at the moment. It can be fiberized, so you can connect it to any type of vehicles, and it can match the cone head of the EcoSub. I'm going to go very quickly over these. This is the success we had recently of developing these selective molecules. Again, this is something we're doing at the same time, using the optical fibers again as another platform of the SPR. So I said 20 pounds maybe for the SPR. This was £1 really. And this optical fiber, the sensor itself, you can see we can wrap it on a human hair. So the black bit is a human hair. It's that small. It's stronger than stainless steel. So again, this is one of the routes we're trying. We have a calibration facility as well for hydrocarbons at the NOC. So we're using a gas chromatographer, and we can create a good multi-point calibration curves. Afraid I have to speed up a little bit. So this is again one of our deployment trial using surface flux and subocean flux. So as you can see, we deploy our sensors on the top. We sample from the water, and then we measure nearby. The same thing I mentioned before, we can be as F any distance from the source of leak. I will go through this very, very quickly. I just want to show this because this is a new program mission that I'm going to talk about it in Marine Autonomy and Innovation Conference, using silicon photonics for sensing. So for all these sensors that I talked about, it took a long time to make it repeatable, robust. Then we tried to investigate these silicon photonics. Again, silicon photonics are these little chips that's in your phones or in your laptops. Actually, it's everywhere. And when I tried to do the same measurements with specifically designed silicon chips, the repeatability was incredible, simply because they are made in high scale, high repeatability scale. Silicon have repeatability factors up to atomic level. But the good things is it's extremely promising. Bad things, I feel that I have wasted lots of time investing in other technologies. So that's where we are at the moment. We have, as you can see, in something that small, you have a laser detector and the sensing element all in one chip. And we can reproduce these chips in thousands in 24 hours, less than 24 hours. So we did the pressure testing for these up to 6,500 meters, and they survived these tests. You can see here in these chips, each chip contains 124 lasers. So you can monitor up to 124 analytes in one single chip. And this is how it's look like when you zoom in. I'm not going to talk about sensors anymore. I'm sorry if I bored you. But I also wanted to talk about the calibration we do, the capability. So we spent a long time on this, trying to know if our sensors are actually measuring the right thing. And we realized this is not something actually easy to do. So although it is kind of old-fashioned calibration technique, yes, chromatographer, getting it to PB levels in order to monitor spills in high accuracy was a challenging task. So we have developed this technique to calibrate as well, and this is one of the NOC capabilities. From what I understand, we are one of the few places in the world who can calibrate or detect some methane samples, hydrocarbon samples in ppb levels. We can also monitor nitrous oxide and carbon dioxide, and that's how our system look like. Thank you so much for listening. I'm just hoping that I interested you in what the future will look like for ocean monitoring. And definitely we need to close some of the bridges between what the future look like and what the present is. I'd like also to thank my groups from both of the OTE and the National Oceanography Center and the University of Southampton, ORC. Thank you very much.
Okay, thank you, Rand. Time for one quick question. Rand will be around as well the rest of the day, but Will?
Yeah, sorry for my complete ignorance of this subject, and
Just hang on a second, I've got a
how
microphone.
ignorant I am. Is it envisaged that different apologies for my complete ignorance on this subject, and you've just emphasised just how ignorant I really am. Is it envisaged that different hydrocarbons have different signatures?
That's very true. So this is one of the advantages of using nanotechnology. So instead of looking at hydrocarbon in general, we're looking at the fingerprints of each hydrocarbon on its own. This is spectroscopy. So the first type of sensors, when we looked with membranes, selective membranes, these have molecules that can actually capture hydrocarbons in general. So we cannot really detect things that are not, within the hydrocarbon range. But when you use nanotechnology, you can look at the fingerprints of each hydrocarbon separately. And again, one of the things that we didn't want to talk about, we can actually also, since we have this capability of looking at the fingerprints, we can look at the isotopes nature of the hydrocarbons as well, each one separately. We had a great success with this recently, but I think I need to get more repeatability from the sensors to promise that we are able to do these type of measurements.
Thanks for the question. Thanks, Rand.